This final experiment in this series uses simple materials and dramatically demonstrates a chemical change. First, we need to mix up a special solution of household bleach, vinegar, and water. The proportions are as follows. For a 10-station classroom situation, you'll mix 1 liter of water, that's about 5 cups, with 200 milliliters of bleach, or 1 cup, and 100 milliliters, or 1/2 cup, of vinegar. If you're doing it singly as a demonstration or students want to try it at home, they would use 1/2 cup or 100 milliliters of water, 4 teaspoons or 20 milliliters of bleach, and 2 teaspoons or 10 milliliters of vinegar. It's best to mix this up in advance so the students aren't working with the bleach themselves. Each student group will take 100 milliliters of this stock solution and pour it into a cup. Then they're going to get a piece of steel wool and submerge it in the liquid. And we'll push it down with a knife. And then we'll put this down and let it sit for about 5 minutes. After we've watched it for 5 minutes, we've seen a color change, so we suspect a chemical change has taken place. Now we're going to remove what's left of the steel wool, and we're going to see that we have this reddish liquid in here. We're going to discard this piece of used steel wool, and then let this red liquid settle for another 3 or 4 minutes. The next step is to pour off as much of the liquid as possible without losing the rust. Then we'll want to mix a lot more water with this to get rid of some of that liquid chemical. And we'll let this sit again for 3 or 4 minutes to let the material settle out. Now, one more time, we're going to pour out as much liquid as possible without losing the red solid material. Now the next step is to filter this. Remember how to use the filter paper. You can cut it out of coffee filters. Make a round circle, fold it in half once, half again, and then put it in a wet funnel. The funnel is moistened in advance to hold the filter paper in it. Now we're going to pour this into a small container and collect as much of the red material as possible. Now your students don't have to pour everything through the filter paper to get enough to use. But once they've poured some through, they can then remove it and open it up and take a look. Here's what they should see. The red solid material is left in the filter paper and the liquid that goes through is clear. The next step is to dry this. The best way to do that is to set it on a piece of folded paper towel and let it sit for another 5 minutes. With the use of video, we've compressed the last 5 minutes and we're ready for the next step. The next thing we do is test this red solid material. It's kind of like a paste now with a magnet to see if it's magnetic or not. And we see right away that it's not. It doesn't stick to the magnet. Now we want to scrape some off with this knife and put it on a spoon. Once we scrape enough off to put on our spoon, we're going to heat it up over this candle flame and change it again from this material into another material. We'll move everything out of the way, light our candle up, and then hold the spoon over the candle flame. And what we're going to do is, once again, have a chemical change. We'll change the chemical composition of this hydrated iron oxide. Hydrated iron oxide means that it has water in with it. One of the things we notice is the change in size. It changes from a red color material to a much smaller black material. I've been heating this now for about 3 minutes. Let me show you what I've ended out with. The size has changed and the color's changed. And when we bring our magnet near it, some of the particles are magnetic. Now let's review what we've just done here. We took vinegar and bleach and water and mixed it together. We formed an acid called hypochlorous acid. The chemical formula is HClO, hydrogen, chlorine, and oxygen. And in fact, we had a chemical change there, but we couldn't detect it. Then we put in the steel wool, and the acid reacted with the iron in the steel wool to form an iron oxide, whose chemical formula is Fe2O3 with water. So it's a hydrated ferric oxide, or rust as we sometimes know it. Then by collecting it using the filter paper and heating it up, we changed the chemical again, and we changed it to a chemical which we call magnetite, whose chemical formula now is Fe3O4, and it's magnetic. The most effective science experiments are those that use materials that are easy to get, produce exciting results, and motivate the student to experiment at home. This activity, paper chromatography, is one such experiment. A little bit about the theory first. We have an ink and we want to separate it. That ink is made up of a certain number of different colored pigments to make it black, say. Let's say it's got 3 pigments, red, yellow, and blue. And we want to separate those 3 pigments. Well, one of the chemical properties of a particular material is its solubility. How well does it dissolve in a particular material? How readily does it dissolve? Let's say that the blue material dissolves very readily in alcohol, and the yellow material doesn't dissolve as fast, and the red material dissolves the least. So all we have to do is somehow get that black ink to come in contact with alcohol and spread it apart. Now we could pour the black ink through filter paper all day and it wouldn't filter the colors out. So we have to try the technique called paper chromatography. Here's how we do it. We get a piece of coffee filter, cut it up into a long strip, put a black dot with a particular color of ink that you want to separate on the piece of filter paper, and then get a test tube and lower it into the test tube. Make sure that the black dot doesn't touch the liquid in the test tube. Now, what kind of liquids can we use down here? These liquids are called the solvents, the material that dissolves it. And as the paper sits in there, the solvent moves up the paper like a wick. This particular test tube has alcohol in it. You could try water, you could try just about anything. Some materials will dissolve in water, some will not. Some will dissolve in acetone and may not dissolve in alcohol. Good examples. This particular piece of paper here has been sitting here for about 10 minutes, and we can see that we've separated the red, the yellow, and the blue that was in that black ink. It's kind of like a fingerprint. Different inks have different pigments in them and different hues of pigments, and you can identify where a particular ink spot came from, what type of pen it came from. It's almost like detective work using paper chromatography. Now, if you want to get into a more advanced model that really gives much more beautiful results, you want to use coffee filters like this. Cut them, open them up and cut like a rectangle out of them so it's got a little tongue that'll bend down, and then tape it onto a plate like I have shown here. I've got this coffee filter stretched and taped onto the plate. The little tongue is bent down into the plate so it'll pick up the solvent, the thing that's going to dissolve the dot. And I've set the dot here in the middle. I'm going to pour alcohol in this plate, just enough to wet the tongue so the material will go up through the paper, and then doesn't just spread in one direction, it spreads outward in a circle. And you want to make sure that you cover this plate and let it sit for an hour or two to let it really develop well, because it has to go over a longer area than it would in a test tube. You're going to get beautiful results like this. Now, this is the same kind of ink that we're using here. Even though the results look different, you can see that the hues are the same and the color content in the ink is the same. Say we wanted to compare some other black inks to see how they compare out. Well, here's another example, a different kind of black ink. From the outside it would look like the same black ink, but when you separate it with paper chromatography, you see that the chemicals in the ink are really quite different. Doing this experiment, the students get to understand not only how to separate particular materials using chromatography, but things that look the same on the outside really are made of different compounds, different pigments in black ink. You might want to try different colored inks. I've been trying just about every pen in my house, and I tried an orange pen, and I found out that orange, as you would expect, is made up of the 2 primary colors, yellow and red. And this particular orange pen has at least 2 separate red pigments in it. Now, what can we do with paper chromatography? How can we work it into a class activity? Well, you could get some different brands of, say, black pens. Make these up in advance, little strips with a black dot of each, and the pen only you know is corresponding to the letter A or B or C, depending on which pen you use. Hand these out to your groups of students along with test tubes and alcohol. Have them do the separation, and then have them go up to the front of the room and from cards that you've previously prepared, try and identify what pen A came from or what pen B came from by trying to match up the separation. This particular one came from a Pentel. And now we've come to a somewhat difficult yet very important concept, and that is the idea of density, or the compactness of a material. It's important because it is a major physical property of all materials. In fact, many times you can identify an unknown material by figuring out its density. Now, how do we go about getting this idea of density across to our students? Well, I like to start by offering up two pieces of clay, a large one and a small one. And before class starts, I put some lead weights in the small one to trick the students. When they come to class, I say, which piece is most dense? This one or this one? Most students will say the large one because they really don't understand what density means anyway. You have a student heft them, and right away the student's going to say, oh, wait a minute, this little one seems to weigh more than this big one. What's going on here? It shouldn't weigh more if it's clay. So right away there's a conclusion drawn. There must be a different kind of material involved here. Either this one's been hollowed out and there's a lot of air in there, or maybe some wood inside, or this one has something heavier in it than clay, like maybe lead weights. And sure enough, when you open it up, you can show them that you tried to trick them. They're starting to get an idea, an understanding of density. That density is more than just weight. It's the amount of space something takes up too. There is a relationship between weight and volume. Now we want to go on to this next part, the rocks. Take a very large rock and take a much smaller rock and ask the students the same question. Which rock is denser? Now right away they're going to realize that you couldn't have taken these rocks apart and put lead weights in them, but yet there's still a problem here. This rock is so much bigger than this rock. It's very difficult to make a comparison. If this big rock was the size of this rock, then it would be easy to do, because we could just weigh the two and see which one weighed the most. So let's hypothetically make the two rocks the same. To do that, we'll get a knife and cut a little cube and pull it out of this rock, and we'll make it about the size of this sugar cube. Actually, it's a little bit smaller, and it measures 1 centimeter in each direction, so it's 1 cubic centimeter. It's a cube that's a centimeter on each side. And we'll do the same to this rock. Cut the little cube out, and this time I've painted it blue. Now we've come to a very simple problem. Which one of these little cubes, which are exactly the same size, weighs the most? That's the densest piece of material. And it's a very simple thing to find out. And that's really all we're doing when we find the density. Now, you're going to say, well, we can't physically cut little cubes out of rock. And that's correct. But how about this? What if we had a graduated cylinder and we took this rock and squeezed it to liquid and let all the liquid pour into this graduated cylinder? How much space would it take up? Well, it just turns out that 1 cubic centimeter, one of these little cubes, is the same as one of these 1 milliliter marks on the graduated cylinder. So now we've come down to a simpler question: how can we convert this rock into liquid? And we go back to that old friend of ours from the K3 physical science tape, the overflow can. We can very easily find the amount of space this rock takes up using our overflow can. Before you do it, have the students make a guess, a prediction. How many milliliters of liquid will this rock take up? And if you want to hold up a sugar cube next to them, let them make a guess. And then when you drop it in the overflow can, you're going to find some interesting results. When I use this rock, I came out to have 82 milliliters of volume, 82 milliliters of space. Right away, someone will say, wait a minute, this rock doesn't equal 82 of these. And if you stacked them up, you'd realize it right away. So we have another problem. If you measure the sugar cube, you'll find that it's bigger, larger than 1 centimeter on a side. It comes out to be about 1.5. And if you multiply those three numbers together, you'll find that a sugar cube is really about 3 cubic centimeters of space, not just 1. So that kind of resolves our problem. The overflow can is the accurate measuring instrument. 82 milliliters of space. The next question, how much does this rock weigh? Well, we go ahead and weigh it on our balance. And this particular rock weighs 205 grams. So if we have 82 of these little cubes weighing 205 grams, how much does one little cube weigh? We've now got it down to a simple division problem. If you can divide, you can calculate densities. The question is, which number do you divide into which? Well, I remember this with a picture of the weight, or to be more scientifically correct, the mass on the top squishing the volume underneath. It's easy to remember with a picture. So the mass, which is 205 grams, is on the top and is divided by 82 milliliters. Once a division is performed, we find the mass of 1 milliliter, or 1 cubic centimeter, and that is the density, usually expressed in grams per cubic centimeter. Now, the students will start to see in a science experiment like this that there's reasons to learn mathematics, usefulness, purposes for some of this stuff. And if you want to calculate density, you have to learn your division tables and learn how to divide. And now we go on and use these newfound skills. We'll take ourselves on a journey to a foreign planet. Before we make this interplanetary journey, you'll have to make some preparations in advance. First, gather some materials like these, and then find the density of each using your balance and your overflow can. And then make some hypothetical names up for each item. Like, we'll call this clay Zorp. And we'll want some distractors in there. Clay's density is about 1.5, so we'll put Zorp down for 1.5, and then we'll make up one like Bleem. Bleem is 2.0. And we'll have the densities and hypothetical names for all of these materials. Then when your students come in, you say, we're going on an interplanetary voyage and we've landed on this planet and we need to resupply to continue our journey. Unfortunately, we don't know the names of these materials, and the only way we can find out is to find the density of the material and then look on the blackboard and find out the foreign name for it so we can ask for it by name. Now, if your students are correct, they'll find the density of this to be 1.5 and they'll say, can I have some Zorp, please? If they're off a little bit, they may come out with 2.0 and ask for some Bleem by mistake, and you can give them something strange, like a bag of dirt. It's a real fun activity, and the students will learn density at the same time. Now let's keep the excitement up and find the density of liquids. Remember, to find the density of materials, we need to know two things: how much it weighs and how much space it takes up. Let's deal with those two questions. How much space does our liquid take up? Well, we just make our own space. Here we're taking exactly 100 milliliters. This is a graduated cylinder, and it measures up to 100 milliliters. You can get them in plastic, or you can get them in glass. If you can't afford too many of these, you can use olive jars. And believe it or not, this 100 milliliters will pour into this olive jar and come right up to the screw thread, so it's a very handy measuring device. Now we know how much space it takes up, we know the volume. How much does it weigh? We can't pour it on the balance, so we have to do an indirect weighing method. First thing you do is weigh your empty container if you're using an olive jar or a graduated cylinder. Find how much it weighs. This graduated cylinder weighs 137 grams. Then you pour the liquid exactly 100 milliliters, and here you want to stress to get exactly 100 milliliters. Pour it into the graduated cylinder, and I've got exactly 100 milliliters, and you weigh it again. If I weighed this again, it would weigh 223 grams, much more. Now we want to know just the weight of the liquid. Good question to ask your students. 223, the liquid in the glass. How much does just the liquid weigh? Well, we subtract the 137 from 223, and the weight of the liquid, the green liquid, is 86 grams. Now we're getting somewhere. 100 milliliters of liquid weighs 86 grams. How much does 1 milliliter weigh? Everybody can divide by 100. Move the decimal point over 2 places, you get 0.86 grams per milliliter. Do you think it's water? Remember, we talked about this. Water weighs 1 gram per milliliter. That's an interesting unit in the metric system. So this is lighter than water, and in fact it's alcohol with green food coloring in it. To continue this activity with your students, they always use that same initial weight, that 137. They don't need to re-weigh an empty graduated cylinder. Have them test 3 different liquids: alcohol, fresh water with blue food coloring, and very salty water with red food coloring. If you do the same calculations, you'll find that I found that the water came out to be 0.99 grams per milliliter, very close to 1, and my seawater came out to be 1.1 grams. By measuring 100 milliliters, you get very accurate results in this activity. Now you can go and handle it the same way as you did with the solids. You can put words on the board: liquids, water, salt water, alcohol, gasoline, paint thinner, some distractors too, and then put the densities after them and ask them to identify the individual liquids. What liquid is this? If they do it right, they'll find out that the green liquid is alcohol. They're identifying an unknown liquid now by finding its density. While we're on the topic of density of liquids, here's another fun activity you can do. Start with some water in a test tube, put some green food coloring in, pour it into a graduated cylinder. On top of the water, add some corn oil. Now, corn oil is lighter, less dense than water, and you want to pour it carefully, and as you pour it carefully, you'll see that the corn oil floats on top of the water. From here we go to alcohol. And I put red food coloring with my alcohol, and once again carefully pour the alcohol on top of the corn oil, and the alcohol will float on top of the corn oil. And the final layer is baby oil. And it's probably good to keep the baby oil clear. I tried mixing food coloring with it and it didn't dissolve real good. That's another lesson in solubility. So we put the baby oil on the top layer, and the baby oil floats on top of the alcohol. We now have a column of different liquids with different densities. Now let's go one more step. Here's a piece of wax, a piece of crayon. What will happen if I drop it in these liquids? We know it floats on water, but will it float on any of these other liquids? Well, you make a prediction. Where do you think this crayon will end up? Let's go ahead and drop it. Drops through the baby oil, drops through the alcohol, slowly drops through the corn oil, and it should end up on top of the water because we know it floats on water, to prove our suspicions right. We're learning more about density. We're finding out that some materials float on top of other materials, and in this case the density of the crayon is less than 1 because that's the density of water, 1 gram per milliliter. There's one more state of matter whose density we must find, and that's the density of a gas. And we need to know those two magic numbers: how much the gas weighs and how much space it takes up, and then of course divide. Now we already did an activity earlier in this tape where we found the weight of the gas that's given off by an Alka-Seltzer tablet. All we need to do is find out how much space that gas takes up, and we got it. Now how are we going to find out the volume of the gas? Well, very easy. We get a drinking glass in our aquarium, fill it with water, make sure there's no air bubbles in it, and invert it upside down. Then we want to quickly and carefully insert the tablet under the glass and let all the gas from the tablet bubble up, and we'll catch it in the drinking glass. We'll see how much gas is given off. There's so much gas in here it's beginning to float and flip around upside down. We don't want that to happen. We want to capture it, get it back around. So you've got to put the palm of your hand on it and flip it back over. Now we've got it. Now all we have to do is measure the amount of space that's in the top of this glass. Well, here's our graduated cylinder, and here's 100 milliliters. What'll this do? Well, let's pour it in. Fills it to there. Looks like it can take more. There's 100, and we'll use this one that goes for 50 and see how much we can pour in from here. Right to the top, and we poured it down to 20. So it took 30 more. So it took 130 milliliters. That's the volume. The weight is 4/10 of a gram. The volume is 130 milliliters. We need to divide 130 into 4/10. That'll give us the density. And the density should come out to about 0.003 grams per milliliter. Now if we look up in a chemistry book to find the density of gases, and we look in particular at carbon dioxide, we find out that its density is 0.002. Now while we're having fun investigating gases, let's take a look at two more exciting experiments. This first experiment brings together a lot of the principles that we discussed earlier in this course. Ideas like chemical change in acids and chemical reactions and properties of materials. What we're going to do is prepare the gas hydrogen, and we're going to use the magnesium that we used earlier in the course, magnesium ribbon, and you want to cut up little pieces, particular lengths that the students can actually measure the length of the ribbon. I like to use lengths that vary from about 1 to about 3 centimeters long. Now when the magnesium reacts with vinegar, the hydrogen in the vinegar is given off. Remember that all acids have hydrogen in them. The way we're going to do this experiment, start with a little bowl like this, and I made these bowls by cutting the bottom off of a plastic cup. Fill the bowl about 3/4 full of vinegar. The next thing you need is a test tube, and the test tube has to be filled to the very top with vinegar. And I like to use a piece of duct tape to put it over the top so I can seal it off so we don't have any vinegar spilling out when I flip it upside down. What I want to do now is flip it upside down, make sure there's no air bubbles in it, lower it into my little bowl of vinegar, and then carefully pull the duct tape out of the way and set this test tube in the middle of the vinegar. Now we want to get our piece of magnesium and carefully slide it under the test tube and have the magnesium react with the vinegar. We're having a chemical reaction here. We see the gas produced, and you'll eventually see the magnesium disappear. I'm going to use a 1 centimeter piece of magnesium, and you want to get it in and under that test tube as quickly as possible. It takes about 10 minutes, and you have to jiggle it a little bit, and as you do, you'll see the gas bubbles coming off the magnesium and collecting in the top of the test tube. Once the reaction is complete, and you've collected all the hydrogen that the magnesium will give off, you want to mark the level with the crayon so you can find it again later on. Then you want to try and save this hydrogen so you can test it. So we're going to use our piece of duct tape, and we're going to slide it back under here and try and seal this thing up as best as we can, and then flip it over again. Now we just have a small amount of hydrogen here, but we know one thing about hydrogen, that it's a very flammable gas. We want to test this idea using a match, and we're going to put a match in this hydrogen, see what happens. It pops or burns, and that is a good indication of a chemical property of hydrogen. It's a flammable gas, so we're studying chemical properties of gases now. Now we want to go to the next step and calculate the volume of the gas that was given off. How much space does this gas take up? Since we didn't lose any vinegar when we pulled this test tube out and flipped it around, we can just pour a liquid into this space to see how much volume that gas was. We'll use this graduated cylinder. This is a 50 milliliter graduated cylinder, and it's filled to 50 right now, and we'll pour it till it goes right to the very top. Stop right there. It's now down to 40. So this gas we collected was 10 milliliters of volume. Now, surprisingly enough, the students will find that the amount of magnesium they used is related to the amount of gas they collected. The longer the magnesium strip they had, the more gas they collected. You're probably wondering, by the way, why we had this crayon mark down here. If the students made a mistake and the vinegar spilled out when they were trying to get the test tube out and flipped around to test the hydrogen, not only did they lose the hydrogen, it went up into space because it's lighter than air, but they also lost some liquids. So in this particular case, what you do is you pour all the liquid out, and then you just fill it up to the crayon mark, and that should give you 10 milliliters also, or whatever your particular measurement was. We want to go on and take the students' data and put it all together as a class. We want to graph it. And the way to graph it is to first put all the data on the board from all of your student groups. The centimeters of magnesium that was used and the corresponding milliliters of hydrogen that was collected. Then you want to graph it. Put the volume of the hydrogen on the vertical axis in milliliters, and mine goes from 0 to 35, and the amount of magnesium on the horizontal axis, and mine goes from 0 to about 3 centimeters. Then you plot the points. You'll find that the points lie about a straight line. You may have some outlying points, and you should probably discuss possible errors in this experiment. You want to find the straight line of best fit that goes through all these points. Now, the theme behind all of this is that when you mix chemicals and you have a chemical reaction, they combine in certain proportions. So you can almost make an approximation of a strip of magnesium that you didn't use, a particular size, and the amount of hydrogen that you would collect from it. Another gas we can make and have lots of fun investigating is carbon dioxide. And of course, the standard technique for making carbon dioxide are the two common household chemicals, vinegar and baking soda. Baking soda's chemical formula is NaHCO3, sodium bicarbonate. And when the vinegar is mixed with it, CO2 comes out of it, the gas. We can tell the gas is there because we see it bubbling, and we know a chemical change is taking place. Now, let's do a couple observations before we actually begin this experiment. First, let's see if the air in here will support combustion. In other words, will this flame continue to burn? As far as I get way down to the bottom of my fish tank, even near the sodium bicarbonate, the flame continues to burn. The next question is, will the flame burn when it's close to this vinegar? We put it in the vinegar. Even very close to the vinegar, it continues to burn. Now we want to go ahead and mix the vinegar with the baking soda and produce the carbon dioxide gas. And I like to use a fairly large tank so all the students in the class can see this. It takes a reasonable amount of vinegar and baking soda to put on a display this large, but it's worth it. You can put a piece of black paper behind it to make it easier to see things. Now, some properties about carbon dioxide. We'll say it's here. We can't see it. We probably can't smell it. If you smell it, it smells like vinegar. It's odorless, it's colorless. It's supposed to be heavier than air, which means that if the tank is open like this, it's still sitting in there. It's not rising out like the hydrogen would. And it's supposed to not support combustion. Well, right away we can check that one with our wood splint. If the carbon dioxide is there, we can lower our wood splint in and see if it'll support combustion or not. And it doesn't. That's a chemical property of this particular gas. It's not flammable. The reason this flame doesn't burn in the gas is because there's no oxygen in there to continue to support combustion. Now, if the carbon dioxide is there, and using the wood splint, you can actually see where the layer of carbon dioxide is. It's right there. We want to try and color it somehow, just like we color clear liquids with food coloring. And a way to color carbon dioxide is to use a match. Try and light the match inside the carbon dioxide. The match will give off all that smoke, and all these tiny little smoke particles will actually color the carbon dioxide gas. Let me show you what I mean here. You can see that the smoke is sitting in the top layer of carbon dioxide. And you can actually rock the tank back and forth to show your students that the carbon dioxide really is there. And even though it's normally a clear gas, you're now able to see it by coloring it. You can actually pour this gas, and you can see it pour off the edge. Another fun thing you can do is get some bubble soap and blow bubbles. And because the bubbles have air in them and the carbon dioxide is denser than air, then the bubbles will appear to float as if by magic on this invisible layer of carbon dioxide. Watch this. Guaranteed, when you show your students how much fun you can have with CO2, they'll all be going home to raid the pantry for the vinegar and the baking soda. There's more things we can do with CO2, so let's go on. Remember some properties we've just discovered about it. Physical properties. It's clear, it's odorless, it's denser than air, it's a very dense gas. And some chemical properties, at least one, is that it does not support combustion. It doesn't burn, or it doesn't allow things to burn in it. Let's use some of these ideas and go on and do another investigation. This time we're going to make some carbon dioxide in this beaker by adding, once again, vinegar and baking soda. Oh. Now we want to make a trough out of cardboard like you see here. Using the principle that it's heavier than air and it puts out fire, let's see if we can blow our candle out by pouring this invisible carbon dioxide on top of the flame. Watch what happens. As you can see, it easily puts out the flame. It's this chemical property, the fact that it doesn't support combustion, which makes carbon dioxide an ideal gas for use in fire extinguishers. Now a student might say, wait a minute, carbon dioxide has oxygen in it. Why doesn't it support combustion? Well, remember that a compound has different properties than the elements which make it up. Now we've looked at two separate properties of carbon dioxide. We've looked at the chemical property, which is its flammability, and we've looked at one of its physical properties, which is its density.